And then if you want to play
We'll be holding this.
The world today is facing a plethora of challenges. Global temperature will be 1.5 degrees Celsius warmer by year 2050. Number of people under famine has increased by 500% since year 2016. Population aging is faster than before. By year 2030, 1 in 6 people in the world will be 60 years old or more. After all, what is our way forward for a better future? In year 2015, the United Nations set up 17 Sustainable Development Goals, SDGs, which identify global challenges we face and call for actions to address so. Solution to these pressing issues require game-changing efforts. At the forefront of international innovation and technology, the PUI Academy for Interdisciplinary Research, HAIR, of the Hong Kong Polytechnic University, PUI, seeks to combine effort from PUI researchers and extensive partners to bring interdisciplinary, collaborative, and practical solutions to these problems. Our mission is to promote, lead, and support PUI's interdisciplinary research to address major societal challenges, to create societal impact of PUI's interdisciplinary research through partnership and interaction with business, industry, and government, and to enhance the visibility and reputation of the university as a world leader in its strategic focus areas through impactful collaborative activities in research and knowledge transfer. To date, the Academy hosts 11 research institutes and 5 research centers, each with their distinguished expertise. With over 400 senior researchers at PUI, our research institutes and research centers lead meaningful research on 3 thematic areas: advanced technologies and manufacturing, good health and well-being, smart cities and communities. Lying at the core of PAIR's research is interdisciplinarity. Interdisciplinary research involves interaction between disciplines, which may forge new research fields or disciplines for further exploration. This is like chemical reactions, that new products are formed as we put different reactants together. Interdisciplinary research is based on shared knowledge and disciplines working collaboratively. This is like a group of healthcare professionals with the different areas of expertise working together towards the understanding and realization of a person's health goal.
Any of those 17 Sustainable Development Goals set up by the United Nations cannot be achieved by the traditional disciplinary research. At PAIR, the members of our research institutes and research centers from different departments join hands together to develop impactful interdisciplinary solutions for societal problems like climate change, energy shortage, food safety, and aging population, etc.
For example, in addressing neurodegenerative disorders, disciplines like linguistics, biomedical engineering, computer science, nursing, and rehabilitation science will join to come up with ways for early diagnosis, prevention, and effective intervention. To protect us from bacterial infection, our scholars in the fields of chemistry, food science, and Chinese medicine work together in studying edible birds' nests, which hold a specific protein with such functions, and work with industrial partners to incorporate so in our skincare products. To build sustainable marine infrastructures, our civil engineers join hands with scientists from chemistry, computer science, and material science, as well as engineers from marine, sensors and network, and mechanics to develop structures that are resistant to corrosion by seawater and sand, and thus suitable for building marine infrastructures. Harnessing the strengths of PUI's research capability and diversity, PAIR engages faculty members, researchers, and students, as well as universities, industries, and community in Hong Kong, mainland China, and other countries. For better technology and innovation, infrastructural connectivity, industrial modernization, ecological conservation, quality of living, and most importantly, to contribute to the Sustainable Development Goals, which benefits transcend Hong Kong, the nation, and the world.
Good afternoon, ladies and gentlemen. Professor Wang, Professor Lee, and also Professor Guo, to this pair distinguished lecture series. Today, I really have a great pleasure to introduce our lecturer, Professor David Pugh, from the University of Minnesota. So, although Professor Pugh looks younger than me, but when I was a student, I really envy him because he was already a professor at the University of Minnesota and was very famous even at that time. So under his own lifetime endeavor, he is now a member of the National Academy of Engineering in the United States. And also today I learned that he's also a member of Academic Seneca. That's very difficult to get one. And he has really a wonderful lifetime achievement in doing research on filtration, aerodynamics, particles, etc. So, well, I have my pair staff prepare a very long introduction here, but I think I will just make it a little bit short because his lecture will be much more exciting. But I want to mention a few things. One, he is also currently a regent professor at the University of Minnesota. It's a very prestigious position. And in his lifetime, he also established a research center sponsored by the industry and currently have over 40 members. And this really gives him a very good financial resources to really produce a very useful work for the industry. So he has been working on making new instruments for measuring air quality, particles, etc. So many of us are using that here at the PUI, which was produced by TSI, Donaldson, etc. And also, I think Professor Pugh is very famous, not only in the US, it's also in the Greater China area. So the president of Hong Kong University, Professor Zhang Xiang, was his former master student, for example, right? He has supervised over 70 PhD and scholars who also become the leaders in different fields, in academics, etc. So in the real application, some of you might know that during the pandemic in Xi'an, there was set up 2 towers to clean the air in outdoor condition. And today I asked him how good it is. They can reduce the particle concentration by 50% in an area over a square kilometer. That's very impressive. And I believe they will continue the effort in New Delhi, India, doing the same thing. Okay, so I just also want to mention that he published over 360 journal papers and hold 42 patents. In the US, to hold a patent is very difficult. So without further ado, ladies and gentlemen, please join me to welcome Professor David Pugh.
I think this chair is too tall. Maybe you can take it away.
Oh, okay.
Yeah. Okay, all right. Okay, sure. Thank you very much, Professor Chan, for your kind introduction. It's my distinct pleasure to come and speak to you about our research in Minnesota. So today's topic is green technologies development for sustainable environment. Okay, I'm trying to get used to this pointer. Okay, so I'd like to first start out by showing you Landsec. Do I need to? Okay. I'd like to first show you Lancet Commission's statement. You know, Lancet is one of the top 2 medical journals. It says pollution is the largest environmental cause of disease and premature death in the world today. 9 million premature deaths, 16% all deaths are caused by pollution. And in some country, more than 1 death in 4 are caused by pollution. Now that 9 million include both air pollution as well as water and soil, but air accounts for 6 million of that 9 million deaths. So with that, I set the research visions of my group to develop green technologies that benefit sustainable environment, which will enable people and the environment to prosper together. We don't have to sacrifice environment for prosperity. So there are 3 objectives. One is to mitigate PM 2.5, VOCs and ozone in urban environment. Second, to reduce CO2 to mitigate global climate change. And third is to provide clean water to achieve water sustainability. As it turns out, semiconductor industry now require extremely clean water and solvent to avoid particle contamination. So here are some of the instruments my student and I developed. The DMAs, differential mobility analyzers. I developed this very early on. And then my student, Chen Daren, and I developed the nano particle version. And there are thousands of this type of instruments around the world, thanks to TSI, who is located in very close to the campus to measure atmospheric pollution and also for semiconductor manufacturing activities. So with that, we're recognized for providing the basic sciences for this ISO standards for particle size distribution, for calibration of aerosol number concentration. This is important because now the Euro standard make use of particle number concentration for the emission standards from gasoline and diesel engines. And they need to use my method to calibrate the instruments. And then my former postdoc and I, we were together developing test methods for nanoparticle filtration efficiency. And some years back, I worked with National Institute of Standards and Technology into certifying 60 nanometer and 100 nanometer particle standards. So as a result of the instrumentation we developed, we find that atmospheric aerosol consists of 2 modes with a minimum here of 2.5 micron. Smaller than 2.5 micron, they are from anthropogenic man-made activity. And for larger size particle, they could be from windblown dust construction activities. So here is some more detail. So you can think of 2.5 micron is the vertical lines here. Smaller than 2.5 micron, those are fine particles from combustion and gas to particle conversion. So it's from a power plant, vehicle emissions. I like to call your attention to the fact that they have lifetime from days to weeks, so they can transport over thousands of kilometer distance. And whereas for larger size particle, they are from wind-blown dust, construction activity, agricultural activity. Those are big particle, so they settle very quickly. So their lifetime is only hours. So they rarely go beyond 100 kilometer. With that in mind, EPA, when they set up the PM 2.5, they consulted with our lab. So you notice that 2.5 is a subscript. That means less than 2.5 micron. 24-hour standard is 35 microgram of particle mass per cubic meter of air. And annual standard, I want to call your attention that as of March of this year, EPA reduced it from 12 to 9. So now all the city need to meet this annual standard. Otherwise, EPA can come in and shut down some factory. So one important reason is that the PM 2.5 is directly relating to death. So the landmark study is the Harvard 6-city study. So they put this medium-sized small cities, measure their PM 2.5 concentration, and look at mortality rate ratio. Compare with P is setting up at 1. P is Portage, Wisconsin, not far from Minnesota. So you see that from 12 for P to 30 for S, Steubenville, Ohio, this result in 30% more death. So it's real. And so I should mention that I checked all the city. As of last year, they are all below 10. So that's why EPA can now set the standard at 9. Now, one important air pollution in the urban environment is the secondary PM 2.5. So you see that power plant produce plume, and they are a good filter to remove the particle. However, they also emit gaseous emission, volatile organic carbon, NOx, SO2, and so on. Upon irradiation by sunlight, it turns into secondary PM 2.5 plus ozone. So you will see that a lot of the time, the urban pollution alert is caused by the secondary PM 2.5. Associated with it is the ozone pollution. Ozone is also bad for human health. So now PM 2.5 is less than 2.5 micron, including a lot of particle in the nanoparticle size range. So when it is bad for human health, then nano size is very bad. However, there's also beneficial consequence of this nanoparticle. So here's a good illustration. This is the soccer ball and 10 nanometer. The ratio 10 nanometer over the soccer ball diameter is 10 to the minus 8. And soccer ball to the Earth ratio is also 10 to the minus 8. So you can think of if you produce a lot of 10 nanometer particle, stuff it in the soccer ball, you create as much surface area as if you were to have a lot of soccer ball and stuff the Earth. So the reason it's important, surface area is important, is that chemical reaction is oftentimes surface related. So the more surface area, you have more chemical reaction. So with that in mind, my former student and I, we developed a electrospraying technique to produce good nanoparticles. So the way that we did it is to drip the liquid through a nozzle, and you see that if it is dripping, you have a millimeter-sized liquid coming out. And now if you put a voltage on the nozzle, as you increase the voltage, it go in pulsating mode, oscillating between conical and round meniscus. And then if you continue to increase the voltage, you ended up with a cone jet mode. Now you see that for cone jet mode, the liquid surface, the liquid will come out from the apex, where you have a lot of electric field, and the liquid particle coming out is nanoparticle size. So you can produce a lot of nanoparticles that way. And my student and I, together, we have 12 patents on this technique. And then a pharmaceutical company, Nanocopier, they were able to obtain FDA approval when they see that the nanomedicine is indeed having higher efficacy as a normal formulation. So there's a major cancer drug, dasatinib, is approved. It's a $2 billion cancer drug. I heard that they are getting approval for more drug production. So they are now making drug in Taiwan and Canada. Now, we are fortunate that many companies like to collaborate with us. Early years, we have a microcontamination research consortium collaborating with many semiconductor industry. And we have graduated a lot of students and postdoc. And then recently, we have, I should say recently, actually for 33 years, we have a Center for Filtration Research, currently supported by 20 companies, and also a large number of students. So because we have a broad scope on our research, so our students coming out, they are very innovative. They are very inquisitive and wanting to acquire new knowledge. So with that, I want to show you a list of my former students, postdocs, include chair professor in Taiwan, chair professor in Virginia, Zhang Xiang, president of University of Hong Kong. He received a master's degree from me and then went on to UC Berkeley. Scott Ernest, director of occupational safety and health at CDC NIOSH. Shunki Che, vice president, Samsung Semiconductors, senior vice president, Samsung Display, LG Display. He will be coming to give a seminar next Wednesday. That's why I have to hurry back. And then Yang Yi, senior director, Applied Materials, the largest semiconductor manufacturing equipment company in the world. And then Huang Jing, he's a professor at ETH Zurich, Switzerland. Many professors in Korea. And the last one here, Shintaro Sato, he's my PhD student from Japan. He is currently senior vice president, director of Fujitsu Quantum Research Laboratories. Now, I don't teach him quantum computing, but he's very inquisitive. His thesis is on semiconductor manufacturing contamination control. And also he did molecular dynamics calculation. But since returning back to Japan, he developed more interest. So he said that now there are more than 100 researchers around the world reporting to him. So for semiconductor manufacturing, we have an Intel project that supported us to look at extreme UV lithography contamination control systems. Now, EUVL is the last top-down technology. So we look at different way of preventing particle for depositing on the critical surface of the photomask. And and we published 15 journal paper within this 3 years period. And a lot of that has developed into industry practice. And we continue to be involved in semiconductor research. And currently, the companies are interested in having us to look at membrane filter that can remove nanoparticle size with efficiency 99.99999%. Because in semiconductor industry, they use a lot of pure water and acid to remove contaminant on the surface. And so it turns out that aerosol technique is a lot more sensitive than the liquid laser counter, those type of technique. So we use aerosol technique to look at membrane filter efficiency down to actually 2 nanometer. We develop a method to make the quantum dots airborne, and using quantum dots to evaluate efficiency down to 2 nanometer. So currently we have just 20 companies supporting our research. You know about the 3M, Boeing, and then we have 4 companies from Germany, Mannenhammer, Freudenberg, so on. And then there are 4 companies in China, Midea, Meidi, and Senda, and Huayuan, and Yancheng Environmental Science Park. And then Shigematsu is a Japanese company, and Korean company, Samsung, LG Electronics, and many other US company. Collectively, they produce 50 billion annual sales of products and cleaning air for vehicles and atmospheric pollutant and respirator. So one of the study that we did is on looking at filtration mechanism, particularly electric filtration. So the fiber suspended in the air flowing from left to right, so that the fiber deflected the streamline. And when the particle get very close to the fiber, it may be intercepted. If it has high momentum, it will be impacted. If it is small, Brownian motion will cause them to be collected as well. And then if you have a charged particle, it can be attracted, particularly if the fiber has a charge on it. So now this is for the case of fiber, mechanical fiber without electric charge. Particle can be collected on a fiber. If you look at the efficiency as a particle diameter, Brownian motion will cause high efficiency collection, but then for larger particle, it dropped down until here, it will come back up because of impaction and interception. Now, the coronavirus COVID-19 particle is 120 nanometers, so very low efficiency. However, if you put a charge on the fiber, and then now the efficiency move up very rapidly. Joe Thompson, my PhD student, wrote a thesis on that. He is now a scientist at NIOSH. And you see that 120 nanometer go from 20% to 80%. So it is not surprising, therefore, to see that in the or this respirators. Now, anything above here are electric media. Electric media definitely outperform mechanical media. So there's no surprise that most of the respirator now has electric charge fiber. And one other good thing is that because it's so highly charged, you can make the fiber further apart from each other so that the pressure drop reduced. That means you can breathe easier. So next, I'd like to just show you that we also are involved with deep learning for predicting filter characteristics. Now, some of the filter, like this membrane filter, they have large and small pore size, and then very complicated. So what our company like to know is their permeability, mean pore size distribution, filtration efficiency. And but the easiest way is that if we have a filter, if we can use SEM to take a picture to look at the surfaces and be able to predict all the permeability filter parameters. So what we did is to involve using machine learning. So here are some of the filter media that we look at. And so what we like is to be able to take images of surfaces. And then there's a geodetic software that will allow us to calculate using fluid mechanics, the flow through, pressure drop, and also the efficiency. So the method that we use for machine learning is using the convolution neural network. So just like here, you are trying to take a look at the leg of this animal and trying to find out what it is. And you take using machine learning to take a lot of images and then doing the machine learning calculation. And then you find out, aha, it's most likely a zebra. So this is what we like to do with filters too. And so we have a filter surface, and we want to get the filter parameters. And the way that we do it is to use this geodetic software. It's a proven software, but it's expensive, like $40,000 a year of license. So what we like to do is to have a surface like this, and then we use geodetic to calculate the flow through pressure drop efficiency as the output, as the real result. And then machine learning will go from this filter structure into the characteristic. So what we did with this particular experiment is to chop the filter media 14,000 surfaces and get the image, and use geodetic to calculate the filter parameters. It's very time consuming. It takes 2 months of supercomputer time to get the results input into machine learning. And then after that, we spent 2 more weeks on supercomputer to get the machine trained. And then after that, it takes only 2 seconds. So if people give you a piece of filter, you take a picture using SEM and then enter into our trained model. In 2 seconds, you get the whole parameters of filter of interest to you. So here you see that we compare the machine learning results with the geodetic results. And then we also obtain filter efficiency. Remember the V-shaped curve I showed you earlier. And then, so we have good agreement with geodetic. And then now we are looking at fibrous media. It's not homogeneous. And so we need to look at chopping the fiber many times in the flat surface and vertical surfaces. And then in the end, and also we can insert nanofiber media within the fiber filter media. So in the end, we can machine train and obtain the results similar to that of isotropic membrane filters. So so this is a power of machine learning, that you can go from many hours of supercomputing to just a couple seconds with a trained model. Now, the next topic of our Center for Filtration Research is development of a bioaerosol sensor. So this sensor consisting of laser going through here, the chamber, and then there's a camera looking at the scatter light from the particle going through. The aerosol go through from left to right. And the whole thing, you can hold it with your hand. And so what happened with bioaerosol is that it can detect bioaerosol from other aerosol particle. So right-hand side is dynamic light scattering. The scatter light is of the same wavelength at the laser beam, which is 405 nanometer. On the left-hand side, we place a lens that take out all the dynamic scattering signal, and only those aerosol that emit induced fluorescence of a larger wavelength are detected. And so here's an example. You can see that on the left-hand side is sodium chloride, on the right-hand side is bioaerosol. And the elastic light scattering, the wavelength blue laser is 405. You see that both sides scatter light. You can actually see the shape of the particle to further distinguish what they are. And then on the bottom side, we have a filter to cut out all the dynamic light scattering. So for sodium chloride, we don't see anything. And for the bioaerosol, we see that the induced fluorescence lit up the screen. Yeah. So you see that the wavelength is 600 nanometer instead of 400 nanometer for blue laser. And then we also are able to, you see the shape of the particle too. And then we also are able to use color to distinguish different bioaerosol. So you see that from blue to violet. So you definitely see different color particles that distinguish what type of bioaerosol it may be. So as you know, bioaerosol accounts for only a small fraction of the atmospheric aerosol. So oftentimes we like to concentrate the bioaerosol so that it can be detected. And this is what we do. This is a virtual impactor that we have a great deal of experience with that. With this virtual impactor, also handheld size, we're able to concentrate the aerosol by 400 times. So magnify the bioaerosol signal. And one of my former student, Kai Xiao in Shenzhen, he developed a medical hospital robot parading the hospital, and then at nighttime, it will pop up with UV light to sterilize the room. But then that's not so good, because you would like the patrol to detect bioaerosol even daytime, so long as there's a bioaerosol. So he talked about wanting to put one of our bioaerosol sensor in here so that it could be parading during the daytime. When you detect bioaerosol, just pop up and then light up the room. Yeah. So yesterday I was able to talk to Professor Li Shangdong about his work, and I'm very happy to see that he looked at the vehicle emissions and bioaerosol right here. And indeed, in the morning when I wake up, I look down there, there are long lines of cars and trucks lining up to trying to go into the tunnel. So can we do something about it? Yes. Here I will show you. You know that we know about the bimodal distribution, but actually when you get to the source, engine emission, you have ultra fine mode right here. And they are from fresh combustion aerosol. Now they are coming in large number so that they collide with each other and can quickly grow into the accumulation mode in here. So now this is important ultrafine particle. I want to show you that here is the distance from the highway. So if you are within 100 meters away from the highway, you see a lot of 6 to 25 nanometer particles. But see, if you go a little bit beyond 100 meter, it drops down because they all coagulate into larger size particle. And guess what? If you compare the probability of prevalent asthma, people living close by, they develop quite a lot of asthma problem. In fact, there's a study in Spain. They find that people, women living close to the freeway has a higher risk of giving birth to children with impaired lung function. So I'm quite sure that there are follow-up study on that, but I picked this up 7, 8 years ago. I haven't followed up on that, but I'm quite sure that Professor Lee know more about this now. And can we do something? Yes. In fact, you see a lot of highway, they are elevated. So you can use the space below the highway deck to install a duct, and then you can extract the exhaust on the side going down to the duct, and then you bring it to a dust collector. Now, dust collector may not be huge size. Nowadays, there are very good dust collector that's not overly large. And then the clean air, you can bring it to the other side and blowing the air continuously around. So now imagine all the people sitting down there, breathing the exhaust particle. Now you have continuous clean air to come around. Now, if you are wondering how can you do it with the tunnel, yes, you can. I see that there are a couple walkway going across the freeway, and you can just bring the pipe up to put it underneath the walkway and down. So you can actually do some engineering design to implement this for your tunnel. And now this concept can also be applied to inside the tunnel. So you just take out the dirty air and then go through a duct and push it out from the other side. And then my wife walked on the central and with a lot of exhaust. Can you do something? Yes, we can. We just put it in the center divide, and then you bring the dirty air from below, and then go to a dust collector and blow the clean air from above. Now, this can also be applied to bus stop. Imagine that you stand in the bus stop with clean air blowing at you. It's not only clean, but also comfort. Okay, now I'd like to go to another topic of large-scale implementation of cleaning the air. So we have worked on indoor air cleaner for local control, also gasoline, diesel particulate filter for source control. And now I want to tell you about the solar-assisted large-scale air cleaning system SALSCS sources for urban air cleaning. And then we are going to work on CO2 removal using this concept. So if we can do all of that, you will agree that we can create a sustainable environment for the world. So the air pollution is very bad, particularly in India, particularly in Delhi. And in WHO said that 140 million people in India are breathing 10 times air, resulting in 1.67 million deaths. So this is what I pull out from the website on that particular day. The PM 2.5 is 550. And US standard for 24 hours is 35. So it's 15 times higher. And so the city mayor said that it seems like we are living in a gas chamber. So I was actually, prior to that, we also developed system. I'll tell you later. And recently, the most polluted city turns out to be in Mongolia. There's in the capital city, Ulaanbaatar, they are breathing 27 times higher level than WHO. Guess what? The last 2 weeks, I have Mongolian celebrity, the Taylor Swift of Mongolia singer came and visit me. And then the Consul General of Mongolia also come to visit me. They want to ask me what we can do. Actually, they heard about our air cleaning system, which I will show you. Now, about 10 years ago, one of my PhD students, Qingfeng Chao, we look at a way to remove air from the city. So the first one is modeling, and you see that we have a glass paneled skirt around this tower, could be kilometer in diameter, and the tower is 500 meters. And then sunlight going through the glass panel warm up the air. Air will rise, and then the inner side of this skirt is higher than the outside. So that as a result of buoyancy, air will be drawn from the side towards the middle. And then right here, before it exits the tower, we put in filter systems to remove the particle, only clean air come out. So this is modeling of putting 8 of the system around Beijing city. The white plume is clean air. You see that it pretty much reduced Beijing PM 2.5 15% in 2 days. Now for this, it costs a lot of money to construct it. So we are fortunate that Xi'an is the first city that built the first pilot unit. I will give you more information. And then later on, Yancheng Science City built a second generation. It can also take out CO2. And then in Delhi, they built 2 units. That's the 3rd generation. Now, this is the Xi'an pilot system. You see that the glass tilting upward, and then the tower height is 60 meters only. And the air rise and push towards the tower. Along the path, we put in filter. This is 3M electric media, low pressure drop, and this is mechanical filter. And now we compare the modeling with measurement. Flow rate is the easiest way that we can. You see almost perfect agreement, except the north side. You know, for the north side, the tower casts a shadow on the north side. So the north side receives less solar energy, so that the north side actual flow rate is not as high as what we predict. And in India, we built 2 units, one in a transportation hub and one in a commercial area. And this is the one in transportation hub. This is railroad. This is MTR. This is bus depot. So every day there are hundreds of thousands of people walking around here. So we cannot afford to push the clean air up there and then the wind blow it all the way around. So what we do is to actually reverse the flow. Now we use blower to pull the air from the top of the tower and then go through the filtration system and then blow it out on a ground level. So, so this is filtration system, and dirty air comes from the top, go through the filter and go through the fan. And we also do modeling to see the blue is the clean air from the tower, and then red is the dirty air. And you see that within this area, it's actually cleaning down to below 50%. And the large eddy simulation shows that this is percent reduction. So even at 1 kilometer away, we could reduce by 50%. Now this is a New York Times actually took a picture of one of the India unit and then comparing Beijing with New Delhi. They said that New Delhi, there's too much politics. Now, the last topic I want to show you is the ocean temperature, the climate change issues. This is like since 1979, or the ocean temperature, higher temperature during the warmer month to lower temperature in the colder month. But last year, since May of last year, the ocean temperature continued to go up above all the averages here, and even this year continue to go up. So you know that it's not good to have ocean temperature going up because, and another reason for the all this temperature extreme is that Canada wildfires release more planet warming carbon than fossil fuel emission from all but 3 countries, China, US, and India. And the emission of CO2 from Canada wildfire is equivalent to Japan. The whole Japan CO2 production in 1 year is similar to what forest fire in Canada. So as a result, it causes climate change, temperature rise, sea level rise, hydrological extremes, droughts, floods, and fire. And the health effects, heat stress, respiratory disease, malaria, cholera, malnutrition, migration. And you see that it costs a lot more money to clean up the health effects, whereas technology will be much cheaper. Now, this is what we can do with the 2nd generation Yancheng sources. And first of all, we make it a lot more attractive. This is all lined with LED, so we can show commercial and we can show even movies, so people can sit around and enjoy it. Now, this is inside a big building because they want to just build it as a pilot plan. And here we make use of water droplet to knock out the PM 2.5. But one benefit is that if you put sodium hydroxide in the water, the resulting sodium hydroxide droplet can take out CO2. And so this drain go to a utility room where CO2 can be sequestrated, and then also the sodium hydroxide returning recycling. And so this is what we have done. Now, Actually, American Physical Society, they also talk about using this direct contact method. What they do is to use a contact tower dripping sodium hydroxide, but they need to use fan to blow air to the contact tower. In the end, in economic analysis, it's not feasible because you are trying to blow the whole world's air to the contact tower. But for us, we use solar energy. Solar energy drives large amount of airflow to the tower. And what do you do after you collect the CO2? My colleague, here's a DOE contract of pushing the CO2 down 7-8 kilometers where there are hot rocks to heat up the CO2, and the hot CO2 come back up to turn the gas turbine to generate electricity. So actually, I went to Saudi Arabia to talk about using 10 of those Beijing large units we do the calculation. We can take out 16 million tons of CO2 per year. Now, Saudi Arabia committed to removing 44 million tons of CO2 per year by 2035. But if they were to install our 10 towers, they can do it in 2-3 years to remove 1/3 of what they commit. And then also, because of the large area for the skirt, we can put PV panels on top of it, and the electricity generated will be sufficient for 500,000 households. So this is what I hope to convince some country to do it. So in conclusion, we have performed fundamental and applied research towards developing green technologies to mitigate PM 2.5, purifying clean water and reducing CO2 in the atmosphere. Our goal is to create a sustainable environment which will enable people and the environment to prosper together. So this is my last slide, actually my favorite slide. And Beijing, forbidden city under a lot of smog, right? So I'd like to superimpose a progress wheel here, driven by 3 gears. The 3 gears are academia, government, and industry. So academia is good to identify sources, coal-burning vehicle emissions, and the effect, visibility, health. When the effect is bad, government can step in to place stricter PM 2.5 standard and vehicle emission standard. And then our company can come in and produce a baghouse and diesel particulate filter, gasoline particulate filter to remove the emissions. And then that will reduce the source. So what we like to do is to have all 3 gears to turn in the same direction, same speed. Let's see if it works. Aha, it's turning. And if you look at the background behind it, voila, you have a clean city. How do you like that? One important thing, a lot of people ask me, what is this yellow gear? Actually, this is the most important gear. In mechanical engineering, we call it the sun gear. This is our planet gear. So what is the sun gear? It's Professor Chen, Professor Lee, you, and me. We encourage the 3 sectors to work together to create clean air for the environment, to create sustainable environment. Thank you very much.
Well, thank you, Professor Pugh, for your very interesting and also inspiring talk. And also thank you for the good management of your time. You know, last night when we were together, he said he needed to add a few slides to address Professor Lee's questions, and he will need 60 minutes. So you have done a great job here. Thank you. So I believe now is time for Q&A. So any questions? One on the back. Oh, we need you to use a microphone. So.
Excellent presentation.
Like the microphone doesn't work there. Sorry.
Thank you very much for the excellent presentation. Is it really cost effective? Is it really green? Two questions I have. Because synthesis process use many toxic chemicals. So in terms of really it is green and really it is cost effective.
So the question is, the cost looks very high, and it might not be very green. So can you give a little bit answer on that?
Actually, the cost is not high at all. The India unit that we built, the latest one, cost about $2 million to build it, and it takes about 15% of the unit cost per year to operating the unit. And you are right. In India, Delhi, the air is so dirty that actually after operating for 2 months, all the filters totally black. And in fact, the pressure drop is so high that it's bending. So there are some leak on the edge. So those are engineering problems. Once we identify the problem, we can find solution for that. And also, you know that most of the filter, high efficiency filter, can have 99.9% efficient. And but then in this type of units, as well as in indoor air cleaner, we look at clean air delivery rate. It's the airflow rate multiplied by the efficiency. Now, instead of 99%, if you have leak, it may become 80%. So you take that into account. So clean air delivery rate is what we are looking for.
When we produce this filter in laboratory, we need to use a lot of toxic chemicals such as hydrochloric acid, etc. So is it this technology really green?
We don't use any chemicals.
For,
It's all fibrous material, yeah.
For example, this aerosol filter, we synthesis in laboratory with lots of chemicals.
You mean in producing the filter?
Yes,
you use
yes.
chemical.
Yes.
Yeah, that's right. So one of the objectives of our center is produce sustainable fibrous material. Yeah. So instead of using strong solvent to make the filter, we are using water to dissolve, for example, PVA. We don't use strong solvent. So, but there are $50 billion of products. It will take a while before people accept it. Yeah.
Okay. Thank you.
Yeah, good question. Yeah, I appreciate that.
Okay, thank you for Professor Pui's lectures. And in the lecture, I found you use the AI for identifications of purpose, and such as machine vision and deep learning to detect the alargos. And I'm a student from the design of the schools, and we also pay much attention on the sustainable development design and to service for this society. So the question is, what else can AI do in the field of sustainable development? And as a scientist, can you give me give us the designer or design students to cooperate or take part in the sustainable development? Thank you.
Yeah, I should mention that AI is quite new. We are also learning. We are we are not at all expert in AI. We're just trying to apply AI to filtration. And of course, you can read news every day. AI is used in a lot of things, speech, transportation, and a lot of activities relating to sustainable environment. So we like to explore more and more of that. Yeah.
Thank you. I would like to ask the professor that in many of the electrical appliances that we use, they also use fire to prevent those dust and mold. But one of the problems is that after we use all these fibers, and then they just throw away and replaced by a new one. Then in the fiber you just mentioned, then what are the components of the fiber so that they can be reusable for future, so that we can reduce costs in the long run?
Yeah.
I think it's a wastage, right? After every time we use the fiber and then those technicians just told, well, throw it away, replace with a new one.
Yeah, yeah. We understand that. In fact, the ocean, there are more and more microplastic in the ocean. Some of it may come from the filter media themselves. So in our CFR, we are also looking at the sustainability issue of how do you make biodegradable fiber and those sort of things. It's coming. It's a big industry, so it takes a while. Yeah, but this is a topic of interest to them. Yeah.
Thank Professor Pei for your excellent talk. So I'm interested in the bioaerosol sensor. So what is the responsible time, for that sensor to detect the virus or bacteria, and what type of virus can it be? Can it detect? Because we have an ongoing project to monitor the relationship between the distance and the survivability of virus.
Yeah, actually, the bioaerosol sensor that I show you, it gives you real-time response.
Yeah.
Immediately you get a signal. We have a very good software that can detect them, classify them, and all real time. So, but there are many different type of bioaerosol, and
Right.
so we like to see some larger bioaerosol, and also the induced fluorescence is in a higher wavelength. So it's still ongoing project, but initial results looks encouraging. Yeah. So it's by no means it's done. It's just we are developing it. Yeah.
So you will send your student to Professor Lee's group later, and then maybe
talk about this morning.
Yeah. Okay. Yeah. Maybe.
Yeah,
because actually that's cheaper.
A really good student working on it.
Yeah, the sensor is cheaper, right? So the distance we want to, put a lot of sensors at different distances.
Only about $200 of component. Yeah, right.
That's good.
And so the student is, everybody know in the department is the best student in our department. Yeah, it's the first year and he's already best TA. It's a sponge that absorbs all the knowledge. So I challenge him to use bioaerosol to detect also the fungi and those mold.
Right.
So it's very difficult, but
Yeah.
I want to just challenge him. Yeah.
Right.
So he actually came to Hong Kong for our CFR meeting since I was on sabbatical last year. So we have 40-some member attending the meeting, and he came first time is outside of Midwest of US. So I think he really enjoyed it because I noticed that on his laptop, he put in Star Ferry. So I think he won't mind coming back again.
Yes, yeah, welcome him to come to Hong Kong. Yeah.
Mhm.
Okay, thank you.
Yeah, and our next meeting will be held in Germany. Man and Hamel will, they have 80 some years of history and they will host us. So we have already 40 some people registering to come. Yeah.
Okay. Yeah. Thank you.
Okay, Professor, on a very interesting talk and quite some of the new progress. I mean, I already know you've been in the field for quite a decade. Just one case regarding about using tower or even about on the roadside, even bus station type. Have we have any tipping point, for example, using kind of your third generation tower for purification on air quality improvement? Do we have a kind of like you have to reach to 100 very severe pollution episode? So that's kind of working more efficiently. So that's kind of like a issue, how we utilize the best technology to deal with a different degree of air PM 2.5 pollution. That's my first question. So what is your
Good, very good question. Actually, the Mongolian, the celebrity, they want me to build 10 units in Ulaanbaatar. And the Consul General, he's smart because he was former mayor of Ulaanbaatar. And he said that it's not good idea to build it right away in Ulaanbaatar because the residents will be restless. They will be questioning you this and that and that. So instead, he said that it may be wise if we just build one unit in the city south of Ulaanbaatar. The air is dirtier than Ulaanbaatar and the population is 15,000. And then I thought about it, it's a very good idea. In fact, we can do a Harvard 60 city type of study. 15,000, you can track the health record for every resident. And then you can do the death before and after the tower is installed. That's the definitive study then.
question is regarding now we are facing, particularly in Hong Kong or in whatever about the GBA area, it's not about very much the heavy pollution, severe about episode. It's actually is a low to medium one, but they still actually away from US EPA for annual like 9 like a microgram per cubic meter. But we can see there's still toxicity, kind of like a health effect. So in a way, we are facing is both PM2.5 and the gas phase. The gas phase majorly maybe not carbon dioxide, but ozone and other. Professor Guo probably more expert is VOC. So how about this kind of a filtration plus a bit of like a remove for the gas phase working together?
Yeah, I have 2 slides, which I removed after last night to insert the slides I thought you might be interested. Let me see if I can quickly find it. Can I? Yeah, yeah. Can you show the all the slides? Yeah, I pushed some of the slides into Q&A. Okay, here, why don't we, hold on. This is a study done by Professor Li Ziyi, University of Science and Technology in Beijing. So he has been CFR investigator for several years. And so I introduced him to Boeing. Boeing is always like 787, they place strict air quality standard. They want to remove ozone from stratosphere. So actually, as a result, he received direct funding from Boeing, and he make use of zeolite to take out CO2. You can take a look after 200, more than 240 hours, the reduced almost 100% ozone. And then he put it on a honeycomb element like this. So now he has a company in Dongguan, producing this, yeah. And then he has a phase 1 study, phase 2 study completed with Boeing. Now they are looking at phase 3 study, implementing it on an aircraft, yeah. And then he also used zeolite to take out VOCs, and also very successful. So I can introduce him to you. Maybe you can go and visit him in Dongguan. Although he's still teaching in Beijing, but his company is in Dongguan. Yeah. Okay. I have many more slides on other topic. So I hope that somebody can ask me a good question so I can use those slides.
Yeah. Any other questions? Oh, in fact, I do have a question myself. You know, I often use the TSI equipment to measure the aerosols. But, you know, a lot of TSI technology is based on light scattering methods, right? You can measure the transient distribution of aerosol number and also diameter. But
Yeah.
on the other hand, I also use the impactors. But the impactors, you know, you can really analyze the particle components because it's in different layers of filters, but you cannot really get the transient information. So how could you? I mean, whenever I ask the two manufacturers, they always emphasize their advantage. But you, of course, you are expert on this one. Can you recommend me which one I should buy?
Okay, I should mention that TSI, their main product is my electro aerosol analyzers.
Yes.
Which is not a light scattering method.
Or not?
They acquire a company doing light scattering. So
I see.
The impactor, actually, Professor Virtual Marple is the basically the most prominent in impactor design. In fact, N.A. Fuchs, the one that people thought is the godfather of aerosol mechanics, he wrote to us saying that how much he appreciates Professor Marple's work, because he is the first one who did the fluid mechanics for the impactor. He passed away, but then his colleague, Francisco Romay, is now working for me. So we know how to design impactor. In fact, the concentrator that I mentioned, 400 times concentrator, is using impactor technology. Yeah. And then we also work with a Finnish company. They sent a postdoc to work with me, no, PhD student to work with me for 1 year to calibrate the impactor. Now the impactor do not collect the particle. They charge the particle impact on the surface, which is connected to the electrometer. So they have real-time size distribution using the impactor. And actually, I was surprised that that paper received like 500 some citation, just a calibration impactor. But then they, in their company, they publicized this paper, so people reference that.
Okay, yeah.
So there's a lot of combination of different technology to achieve the purpose, yeah.
Okay, great. So we have a time for just one last question. Anyone wanted to ask? So if not, well, let's thank Professor PUI again for his wonderful presentation. And now we'll ask Professor Wang to present a certificate to our speaker. You two take a photo first. Okay, I would like to invite Professor Lee, Professor Guo also to the stage. We can take a photo together. And also, I want a photographer come to the front and take a photo for all of us. Is this possible? Yes. Okay, so we sit down there. Take all the photos. All right. And I would like to thank all of you for coming here today, and especially those who ask questions to make a contribution to this lecture. PAIR organizes distinguished lectures and seminars from time to time, so I will encourage you to come back again in our next lecture. I believe next month we have one seminar with a speaker from Israel who will talk about the impact of AI in the last 2 years. So it sounds a very interesting topic, which will fit everyone. I will encourage you, especially coming back. Okay, thank you.